Hey guys, welcome back to the channel. Um, I made a video on graphs. So this is a data structure and algorithms tutorial type video. Um, it's made for people who have no experience in graphs at all when it comes to data structures and algorithms, and they're learning graphs for the very first time. This will teach you all about the foundations of graphs, as well as BFS, DFS, and cycle detection using BFS and DFS. I've crammed it into all one video, so this one video should get your fundamentals really strong. And I'm gonna make another video for advanced graph topics like topological sort, Dijkstra's, etc. So this should be like your beginner video if you don't know graphs at all and you really want to study graphs for DSA or for computer science in general. Hope you enjoy. Cool. So, firstly, what's a graph, right? A graph, typically in the way you would, use the term in a computer science context, is a series, whoops, a series of connected components. It's kind of like a network, if you will. Um, Especially when you talk about computer science, uh, these DS and algo structure, DS and algo. Usually, I mean, pretty much all of the time, this is what a graph represents. A graph does not represent an XY axis, whatever stuff like that, in case you're absolutely new to this topic. But this is what a graph is. It's a series of nodes that are connected to each other. That is literally what a graph means in computer science. Now, why do we care about graphs? Um, we care about graphs because all data structures in computer science are used to represent information in a certain way, and a graph is such a data structure which represents certain information in a way that no other data structure really does. So, if you were to describe a road network, you open Google Maps on your phone. Well, Google Maps, if you had to sort of condense it into uh, a fixed resolution of cities and roads and stuff like that, and simplify the amount of data you see on the app, it's a graph, right? There are places and there are distances between the places. If you were to represent a social media network, meaning you wanted to represent who knows who on social media. So this person is a friend of this person and also a friend of this person, and these two people are a friend of this guy. Like, if you wanted to represent that information in a data structure, you would have to use a graph, right? It's difficult to represent information like this in any other data structures like an array, a linked list, I don't know what, a hash map, etc., etc. There's really like no good way to represent that information, and so the best way you can sort of encapsulate all of that is using a graph, right? So now, um, now that we've talking about what a graph is, I'd like to talk a little bit about how a graph is represented in computer science. So usually I drew out this diagram for you, but you're not gonna draw a diagram with a pen and paper in front of a computer, right? If you had to literally, like, if these nodes had numbers on them, and you had to sort of represent this in a manner such that the computer understands it. And the computer is like this giant machine that just gets zeros and ones. You can't use a diagram, right? The computer doesn't really know what you're talking about, and you can't get your point across. So when you talk in terms of representing a graph, meaning when you talk about, hey, look, I'm gonna give you like something, and that something should tell you that the graph looks, whoops, that something should tell you that the graph looks like this. It's usually in one of two ways. One of the ways is called an adjacency list, and the other one is called an adjacency matrix, right? So these are fancy ways of basically representing this data structure in a way that the computer can understand. So the adjacency list basically says that, okay, so we're gonna go through every node and we're gonna note down the neighbors that each node has, right? So the adjacency list and the adjacency matrix encapsulate the information that is already present in this graph, meaning if you have the adjacency list or the adjacency matrix, you can reconstruct this graph, right? This is a visual representation. Think about that as more of a coded representation or something, right? So the adjacency list works like this. It's basically a list of nodes of the graph, right? So we have, I think, 10 nodes. So I'm just going to list all of them out here. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what each of these 10 nodes represent is they're going to point to an array of the neighbors that they have. So 1 has just one neighbor, 2 has 3, 2 has 1, 3, and 4, 3 has 2, and you get the idea, right? 4 would have 2, 8, 5, and 6. Okay, so I've written out the list. So like 1 has neighbor 2, 2 has neighbors 1, 3, and 4, 3 has neighbor 2, 4 has neighbor 2, 5, 6, and 8, 5 has neighbors 4 and 7, 6 has also neighbors 4 and 7, and you get the idea, right? So this is called an adjacency list representation, right? And the really neat thing about it is that you like once you have this representation, you can kind of go back and build out the the graph, right? But there is something I'd like to mention here, right? That you sort of have to look at something here, that 1 has neighbor 2, right? That also means that 2 has neighbor 1. So if 2 is in 1, then 1 has to be in 2, right? This is common sense, pretty much. But there's something I didn't tell you about the graph over here, which is, well, this graph is an undirected graph, right? So think of this as a road network where you can go both ways in the network. So you can go to like 1, 2, 3, but you can also go 3, 2, 1, right? So it's like saying, can I go from 1 to 9? Well, yeah, I can. That's pretty easy, right? But what if instead of each edge in the graph being a two-way street, what if they were one-way streets? What if there was a sequence to the ordering of these nodes? Now, can you go 1, 2, 3? No, you can't, because 3 goes to 2. You're stuck here. You can't really reach 3, right? So this, what I've done right now, this is called a directed graph, right? Because you have directions in the graph. It's pretty simple. The edges of the graph have directions on them, right? What I showed you in the beginning of the video before I gave the directions, this is called an undirected graph, right? Because it's a two-way street on each edge, right? So why am I talking about directed graphs? Well, if I make this graph directed, you're going to notice something change in the adjacency list representation. So as you see now, 2 is a neighbor of 1, but 1 is not a neighbor of 2 because you can't go this way. Now, the adjacency list, instead of representing just adjacent neighbors, they represent, well, can I go to 2 from 1? Yes. Then 1, like the thing on the right hand side represents all of the places I can go to from that node, all of the reachable places, right? So it's like 2 would appear here, but 1 would no longer appear on this thing because you can't get to, in fact, 3 would also not appear because you can only go to 4. Whoops, you can only go to 4 from 2. And then from 3, you can go to 2. But now see, from 4, you can only go to 5 and 6. Well, I missed an edge here. Let's say from 4, you can go to 5, 6, and 8, but you can't go to 2. So you'd sort of, you would remove that from here, and then all of the rest of it would represent, you know, where where you can reach from that area. Now you can make it even more complicated. What if you have weights on the edges? Meaning it's let's say you're trying to represent a map. You're trying to represent a 2D map, a road network using the graph, but you have weight on the edges, meaning let's say each node is a city, and to go from city 1 to city 2, you need to travel 3 kilometers, but to go from 3 to 2, you need to travel 4. You put a 5 here, a 2 here, a 1 here, a 10 here, a 5 here, whatever. So what if you had weights on the edges, meaning going from one node to another node has a cost, right? A super easy example would be just the length of roads between cities, like the one I was just talking about. And you could use this for other cases as well, but you know, now that we have a weighted graph, how would we represent such a weighted graph in an adjacency list, right? So an adjacency list, currently, if you look at the one we have right now, it just has, so like one just has two in it, right? But here, instead of just putting a two, you would put in a like a pair, a tuple, saying 2 comma 3, right? So here the first element in the tuple is the city index, and the second element is the weight of the edge, right? So for 2, you would have 4 comma 5, right? And essentially it's the exact same thing as whatever we just did, but for each individual like element, you would just comma and then add the weight, and you'd like make a tuple. So if you don't know what a tuple is like a pair of two, index 0, index 1. It's two numbers, it's a pair. You would represent them as an array of pairs instead of an array of integers. So everything here would be a tuple, right? So that's what a weighted graph looks like, right? Now, cool. So we've spoken about the adjacency list and graphs. Now we'll talk about the adjacency matrix, right? The adjacency matrix represents the same thing that the list does, right? So this is a 1 and a 2, so this is a 1 and a 2. So 2 has 4, here 2 has 4, right? So it's like saying, instead of this format, you have a matrix, and then 3 has neighbor 2, so like this has the neighbor, right? So you could, it's basically the exact same representation, but you're just so 4 has 5, 6, and 8. Uh, that's wrong, isn't it? Yeah. But ideally, what's happening here? Wait, I think I've made a mistake in the way. Oh yeah, it's because I reversed these edges for the cyclic graph, right? So now 4 would just be 8. Well, anyways, the what I'm trying to get at here is that it's essentially the same representation, but we are just using a matrix to represent this concept, right? And so now 4 would have 5, 6, and 8. So it's the same thing. We're just using a matrix to represent it. Typically, this is like you're wasting a ton of space because most of these are like zeros anyway, and might as well just use something like this. And it's just like cumbersome. So usually in problems, uh, you're never gonna see an adjacency matrix in a question. You're only going to see adjacency lists. And the way you would represent like weights, if you had like a weight or something on the edges, well, instead of putting a 1, you could just put the number here. So this would be 1, and then 2 to 4 is 2, so like 2 to 4 is 2. And then 3 to 2 is 3, so 3 to 2 is 3. So you just put the number at that area, and so you see it's not hard to represent a graph using a matrix, but it's more like saying this representation is like a fluffed up version of this. So most people just use this, and I know I used arrows here. So what does that mean? How would you actually represent this? Well, it's not hard. You would represent this in a dictionary. Usually I code DSA in Python, so this would be a dictionary where these are the keys and these are the values. The keys would be unique if you think about it, right? And so you sort of get the idea, right? How you would be able to represent something like this in a matrix. These would be the rows, these would be the column indices, and you just put like a 1 or the weight there. Not hard, right? Awesome. So we have now covered representation of graphs, right? Now we're going to talk about, like, so you have to ask the question, right? Let's say somebody gave you a graph. Let's say somebody gave you something like this, right? Like, what would you really do with something like this? Like, what's the point of this data structure, right? Well, it certainly stores a particular kind of information, but then what would you like to do on that information, right? So if you think about a road system, if these were cities and you were navigating, like you can go from like 1 to 2 to 4 to 8 to 9, right, on a trip. What do you do when you open Google Maps? You put a start and a end location and you hit play or the button, right? Navigate. It shows you the map. So essentially what you're doing is you are navigating the graph, right? You are moving through the graph, right? If this, well, a directed graph wouldn't represent like a social network, but if you imagine an undirected graph representing a social network, then maybe you'd want to see, hey, like how many how many mutual friends do two people have? Or like how many people are connected to each other through a maximum of a link of two, so a friend of a friend, right? So when on Facebook, when you have the option to say make visible to friends only, to friends of friends, and then to all, well, that's like a graph algorithm. If it's friends, it's to all of the neighbors who are at distance 1 to you. Like forget that this is a directed graph for a moment, but then if like 2 had friends 1, 3, and 4, that would be two's friends. But if 2 selected friends of friends in the visibility on Facebook, well, that would mean, hey, 1 and 3 have no other friends, but then it would also be visible to 8, 6, and 5 because 4 has those friends. So you navigate the graph, right? That's usually what you do in a graph. You navigate the graph. You move your way through it to find something, to look for something, right? That's usually what you do with a graph data structure, like just how you would iterate over an array or try and look up something in a heap or a hash map, right? You would navigate through a graph. That's why the data structure exists, right? Awesome. So now, how do you navigate through a graph, right? Well, you're going to say something like, oh, so, well, you pick a starting point and then you just go from there. Like I can go to like here and then here and then here. That's a path, right? But then you got to also go here, 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 here. That's a path, right? But then if I just gave you like a problem statement, like tell me, hey, so you're at 1, tell me the farthest cities you can reach, or like just tell me everywhere that you can go from 1, or like you start at 1, tell me all the cities you can visit if you start at 1, right? So that would be you can visit 2, you can visit 4, 8, 9, 6, 7, and 5, right? But then how did you just do that? Like you visited it like step by step, right? But then like would you how do you know? I mean, it's like if someone told you to do it, you would do it, but there's actually a sequence of steps, like an algorithm. It's like you're already doing the algorithm, you just don't know you're doing it. It's like sorting. If somebody gave you like a handful of Uno cards and told you to sort them, I think you sort them using what's called insertion sort, but you just don't know you're doing it. It's like it's the default sort of algorithm the brain comes to, just like searching for a word in the dictionary defaults to binary search. You don't know you're actually doing binary search, but you actually are. Like no one's stupid enough to flip through every page in alphabetical order till they find the word, right? So when you do this, you can take two approaches, right? You can be like, okay, I want to go step by step, meaning, okay, so I can reach one, two from one. That's awesome. I can reach four from one. That's awesome. Now you could either go, hey, I could go like eight and then nine, meaning you go all the way to see how far you go. Or you could take it step by step and be like, hey, so from four, but then from four, I could do both eight and six. So that's obvious, right? Well, then that means I can get both eight and six. And then from eight, I can get nine. And from six, I can get seven. So now I have nine and seven. And then from seven, I could do five, which is cool. But I know the way I explained this maybe sounds dumb. You're thinking, okay, like why would someone do that? Why not just travel? It's that, well, for example, uh if I sort of it depends on the problem statement, I suppose, right? But instead of asking you all of like all the cities that I can reach from one, if I asked you how many cities can I reach, uh, like just like for example, let's just say that each of these cities had like a distance of one. Everything was one, right? If I asked you, hey, so how many cities can I reach at a distance of three from one, right? So uh, well, your answer would be so one, two, three, two, three, two, three. So your answer would be five, six, and eight, right? But then in this case, if I had like if I did one, two, four, one, two, four, eight, and then nine, and then realized, hey, I actually overshot because like I'm at distance four right now. I need to be at three. That's fine. And then I went this way, and then I overshot again because I need to be at distance what like four right now, and I'm at three right now, and I'm at four. I overshot again, and then this. Well, the thing is, like, it doesn't look that different, but you did one, two extra calculations in this sequence. Whether if you had just done like step by step, meaning like one to two is one, two to four is one, and then four to one, two, three, and you stopped there because you're at three, then you would have zero extra calculations, right? And this is a very small graph. It's a very simple graph. So perhaps this doesn't seem like a big deal, but if you had like a massive, massive graph of like thousands and tens of thousands of nodes and edges, like certain algorithms or certain like this problem statement would be more quickly solved if you just stopped at length three instead of like just trying to explore um, to see how far you can get, right? Because you just save extra iterations and extra loops. So certain problems are better solved like just navigating through the graph directly, um, and certain problems are solved just going all the way first, right? So now we're going to talk about the two, I guess, main algorithms for graphs. So one is, oops, one of them is called depth first search, right? Depth first search means you go all the way first. This is meaning you go as deep or just as far as you can in the graph first, and then you try other stuff. And then breadth first search means that you want to traverse the graph step by step, right? You want to see all of the possible combinations that you can go at the next step, and you want to do all of that. It's like uh, a depth first search problem might be, can you reach from node A to node B, right? But a breadth first search problem might be, just for the sake of example, like let's say a virus is spreading between cities, right? And it can spread to a neighboring city in one day, and you had 3 days. How many cities does it spread to? It's very similar to the problem that I just talked about, but certain problems like that are better solved using breadth first search, where you go like, just imagine like the breadth of the graph step by step instead of like following one branch to completion. So I'm going to give you some code for the breadth first search and the depth first search, but there are two things you need to know about these algorithms. So the first is that when you sort of do these navigation techniques on a graph, you usually have this this is important, right? So there is like something, okay. So if I asked you the question, how would you write the code out for depth first search, meaning you want to go all the way, how would you write the code out, right? Well, you'd say, okay, so in this sort of diagram, we go here, 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 here. But let's break that down. What are we doing? We went from 1 to 2, 2 to 4, but look at 4. 4 has 3 neighbors, 5, 6, and 8. So we chose 8 first. We went to 8. 8 has 2 neighbors. We chose 9 first. We go to 9. So what we're doing at every step is we're saying, find me all the neighbors, pick the first neighbor, go there. That's the step. That's what you did here, here, and all the other nodes, right? So that sequence of steps you kept repeating at every node until you reached a node that has no neighbors, right? So what you would do for a depth first search is that you would, since the same sequence of instructions just get repeated, uh, you would use recursion, because it's like the function is calling itself, right? You could ask me, well, if the same sequence of steps are being repeated, why not just use an iterative approach? You're going to see very soon in the video that an iterative approach far more like makes sense. It's a lot more easier. Like when we use the iterative approach, we sort of end up doing like a breadth traversal. Whereas if you wanted to do a depth traversal first, it's just much easier to implement that using recursion, because recursion would just like do your job for you, right? So depth first search, well, typically I would like to mention here that especially for depth first search, well, especially for all of recursion, you have a separate recursive function, right? So any recursion problem you solve, like dynamic programming, whatever, typically you'd make a helper function and then pass your stuff, your data to the helper function, and then the helper function would be the function that calls itself. You wouldn't usually do stuff to the main function of the program, right? In the editor. So similarly, depth first search also has a recursive function. So we're gonna just write that out here. We're gonna do, I'm using Python syntax. Our depth first search, our helper function is called DFS traversal, and we're gonna take in vertex. So vertex means node, right? And what we're doing is we're saying, let me give myself some room. Okay. What we're saying is, oh yeah. So now as we begin to write this, a recursive function, you run into the problem that this is a directed graph, so that's fine. But if you had an undirected graph, 1 would be the neighbor of 2, and 2 would be the neighbor of 1. So the first neighbor of 1 is 2, but the first neighbor of 2 is 1. So the function would go to 1 to 2 to 1 to 2 to 1 to 2, if that makes sense, right? You said go to the first neighbor. Well, then can't I just go back to where I came from? Because technically where I came from is a neighbor, right? You just keep going back and back and forth, right? That's an extremely stupid thing to do. It would just, your algorithm would just break. It'd be stuck in an infinite loop, right? So in order to prevent that, you would need what's called a visited array, right? So you would need a visited array because you don't want to go back to where you came from. That's what the visited array does, right? So that's why you need that array. But I'd like to mention that if you're working on a directed graph, meaning you can, so like 2 is the first neighbor of 1, but 1 can't be the first neighbor of 2 because it's a directed graph. If you're working in a directed graph, you don't need the visited array because you can't go back, right? So the code I'm writing here is for an undirected graph, but basically for a directed graph, you would just not use the visited array. I'll explain shortly. So essentially you would, okay, so here we have, let's just imagine you have the array. I'll fill it out later. You would say if vertex not in visited, you would let's say what our code does is our code just prints the traversal. It prints the sequence you're traversing. So you would go print vertex, so you're printing the one you're at. You would do visited dot add, yeah, for, let me just to like not confuse anybody, let me write the main function here. The main function is, I'm writing it below the main the other function, right? So let's call the main function just DFS, where the recursive function is DFS traversal, right? So the main function would be, well, you would first initialize the visited array, right? It's empty because you haven't visited anything in the beginning. And then you would do, interesting question, right? An edge case to all of the graph stuff I've been talking about so far. What if a graph exists, but the graph looks something like this? What if after this you had nodes 11 connected to node 12 and you had 13 who just didn't have any neighbors, which means you can't really reach 11 from 1 because nothing exists, and you can't reach 13 at all because it's not connected. It's not connected to anybody, right? How would you traverse this graph? Like if I told you, like, so this is your graph, because think about a road network. Maybe there's like a river here or something, and you can't go. How would you traverse the network? You can't. You can't traverse the network, right? What if you need to? What if the problem statement of the program is, give me all cities at a distance x from the target city, right? Where the target city is the input. And so in our examples, we were using 1 as the target city, but it could have been 3, it could have been 8, could have been 7 from where you started, right? Doesn't have to be 1. So what if the target city is 13? Like, well, the answer would be 0. You can't go to anywhere from 0. So the number of cities at distance 3 from 13 is 0 because you can't go anywhere. But how would you know that? Because 13's not connected to the graph. What I'm trying to say is like use your as you traverse the graph, right? If you traverse from a point, right, you would never visit 13. So imagine the program was, yeah, tell me all of the cities I can visit at a distance of 3 from each city. So all of the cities in distance 3 from 1, from 2, from 3, etc., etc., right? So like one would have maybe it would have this, like at distance 3 it'd be like 5, 6, and 8. 2 would have 7 and 9 and whatever, right? Something of that sort. But then 11 wouldn't have anything because you can't go 3. 13 wouldn't have anything. This wouldn't have anything. This wouldn't have anything, right? But then how would you like explore that, right? How would you explore that? So this is called a disconnected graph, I guess. So it's just basically saying, hey, certain components are not connected. That's all it is. Nothing fancy. But the way you would solve that problem is by using a for loop. You would say, hey, look, if you want me to check every node in the graph and see where I can go with it, I'm going to check every node in the graph. That's common sense, right? So you would run this throughout, right? But the thing is, the visited array is common. The visited array is not reset every time you run, meaning what the code does in this example is that it just prints the cities in a sequence that you can travel them in. It's not super complicated, but it just ensures that all of the cities get hit, right? So uh, now you know that you try and like start your journey at every city, right? But if you start your journey at a city, you would first want to check, have I even been here before or not, right? So this sort of like the simple version here of the basic DFS just sort of solves, hey, traverse all the cities in a manner that you can, right? Something of that sort. Print the DFS. So in that case, you would firstly check, have I even visited the city before? If not, I want to go here again. And well, if I don't want to like make it confusing, this code is specifically for undirected graphs. As I said, directed graphs don't need the visited array, but so if the graph looked like this and I said, okay, how would you traverse the graph? Like just show me the way, right? And then you would start at a node and you would say, hey, have I been here before? If I haven't, well, cool. I am here now, meaning I have visited the city, and then I'm gonna pick all its neighbors, um, and I'm gonna go there, right? So here self.graph basically means the adjacency list representation. So like self.graph vertex, so like self.graph 1 would be this, self.graph 2 would be this. So for neighbor in self.graph vertex means that like this is neighbor, this is neighbor, this is neighbor, etc., etc. You would pick the first neighbor that you have, or you would iterate over the neighbors, and then you would call the DFS traversal, right? So what that looks like here is you go, let's say you go like here, then you go here and then here and then like that. Well, you wouldn't go back because this is the parent. We'd go like this. That would be the DFS reversal. We're trying to go as deep as you can every single time, right? And so that's what that graph would look like. Now, let's talk about breadth first search, right? So what would breadth first search look like in this example? So the breadth first search would look like a level by level. So it would be like it would be like this first, and then like that, and then like that, and then it would end basically because you're all at the same level. So all of like this is at level, let's say 1, this is at level 2, these are at level 3, these are at level 4, and these are at level 5. So it would go level by level, right? And like I said, DFS uses iteration, but breadth first search uses a queue. Like it uses like, sorry, DFS uses recursion, but BFS uses iteration. So BFS uses a for loop, right? But now we sort of have the problem of like, how do we keep a track of like what to do next? Because the recursion is just so nice that we just schedule all this, like this like a for loop here, but we just like schedule all the stuff onto the recursion stack, and the stack just keeps the track of what to do next, right? So it's like the stack would know that, hey, look, like let's say we went here, the next thing would be there because of the for loop that we had, and then the next thing would be there and there, and after this it would be this because of this for loop, right? Uh, and you know the for loop is recursive. But the breadth first search is like, okay, cool. So we got here. Now we would need to go like, so 2 has neighbors 3 and 4, right? Awesome. But 4 has neighbors this, and this. But then at this point, how do we know that the next thing we're supposed to visit is 10, 9, and 7? Like 10's a neighbor of 8, 9's a neighbor of 8, 7's a neighbor of 5 and 6. So like, who keeps track of that stuff? That's stored in a queue. It's saved in a queue, right? So I'll write out the algorithm for BFS. Since BFS doesn't require recursion, you can just do the whole thing in one function. You don't need like a helper function for BFS. The visited array would be present in the function, right? Because of the way the algorithm's implemented. So like DQ is just like a queue structure. It's a library in Python, and then you would add the first thing to the queue, right? But you also add it to visited. Wait, why did I put a? It also added to visited, and then what you would do is while queue. So here queue does the same thing the recursion stack did for you in DFS. So while you have something to explore next, you would take that element. So the way you would take an element from a queue is you would just pop it off the queue, right? It's first in, first out, yeah. And so pop left is just like the pop function. Don't be concerned with that too much, but you pop it out. And so here, once again, you would print the element because this is the basic like function that just prints the thing. And you do for neighbor in self dot graph element. Just once again, just the adjacency list representation that we used. We're going to do if neighbor not in visited. We're gonna save it. So we're gonna be like q dot append neighbor, and we're gonna also do visited dot append neighbor, right? So like, I mean, note, you don't have to do the visited dot append here. You could also do it like here. It's the same thing. Um, yeah, and then, but like, don't try and like memorize the algorithm too much. Just sort of try and understand what's happening. I'm trying to just get the intuition across to you. So it's like you would do, you start at a node, right? And you start at that node, and then you're like, hey, so while the queue has something, you pop it off the queue. So now the queue is empty, but you have one. And then you want to go to all of the neighbors of one. And if those neighbors are not visited, you want to add them to the queue. So like it's empty in the beginning, obviously. So like you would pop this off, and then the queue would just have two. You'd pop two off, and then you'd have 3 and 4 added there. Then you'd pop three off, no neighbors, nothing. You'd pop four off, queue is empty again, but now you'd add 5, 6, and 8. Let's say you pop in whatever sequence, right? Let's say you pop 8 off, you would add 10 and 9 to the queue, but be aware that the queue already has 5 and 6 in it because it's first in, first out, right? So the queue would now look like 5, 6, 10, 9, and then you would pop 5 off first because 5 was in the beginning of the queue, and then you'd add 7 over there, so you'd be like, now it would be 6, 10, 9, 7. So the interesting thing is it sort of maintains the levels, because level 1 items would be first, level 2 items would be second, 3 would be at the end, and 4 would be after that. So you are exploring them in the sequence of the queue because they're getting added to the line in the queue, and so the first ones are all bunched in levels. So that's the BFS, right? And I know you're thinking that, hey, look, why are there two functions here? This is recursive, but like you had a parent for loop here. Why don't you have a parent for loop there? Well, the thing is, like, I mean, yeah, you can. Um, you can. I mean, I'll add the code to the next page, but you should in fact definitely have a parent for loop that just says uh, for vertex in self dot graph. Well, I understand now that you would need, I suppose. Well, no, the visited array can be shared. It can be shared, can't it? It can. Okay. So the same code for DFS would be instead of doing the visited array here, you would do the same. Sorry, you would do visited is nothing for text in self dot graph. Here you would do BFS traversal, and you know what? You would actually pass in vertex and visited, right? Um, yeah. So like you might have to tweak the code a little bit. So obviously now like this line shouldn't be here, and then the function definition will get modified. Now, what happens when you want to do BFS and DFS on a directed graph, meaning uh, your graph isn't like, I mean, if your graph was like directed, how would you do a BFS and DFS? Well, it's very easy. You have to remember that in a directed graph, you can't go back the way you came. You can't go back. So essentially, you just don't need the visited array. It's very simple. So for the DFS, what you would do is you don't need this. You just trigger it from here. You don't need this check, right? You don't need this anymore. You'd print. So you would sorry you would print it, and then you just explore. That's it. Your the whole visited all of the code corresponding to the visited array would just be not needed, because just simple recursion, just explore. And for because like you don't need to keep track of what you've seen so far, because like think about it, like you can only go in one way, right? So you don't really need that, right? Whereas for BFS, you don't need this. Sorry, whoa. You don't need this anymore. Um, you don't need this anymore. You just trigger it from every area, uh, and it should work, right? It's You can only go in one direction, so you don't really need to. You don't need that check for directed graphs, because it's just taken care of if you um, understand the logic, right? Now we're going to talk about uh, trying to detect a cycle in the graph. So detecting a cycle means detecting something like this. Well, it's not a cycle here, but if uh, if I were to, I guess, draw a graph like that, with a graph of a cycle in it, right? So cycle detection is a very useful algorithm in graphs. You can you might need to use it in a bunch of places. So how do you detect a cycle in a graph, right? Now you can navigate your way through a graph. You can explore a graph using BFS or DFS. So you can find a cycle in the graph using BFS or DFS. Whereas like in like this particular example, the DFS might be this, that, and that, where the DFS sort of found the cycle in terms of exploration, and the BFS might be this, this, and then like there, and then this, that, technically. Where so here also eventually you found that cycle, right? So you can find it both ways. I'm gonna write out the code and explain the two, right? What does the visited array do? The visited array prevents us going back where we came from, correct? The visited array lets us be like, hey, so you go here because you found a neighbor, but then this is also a neighbor of this, but you can't go back, right? Because you've already seen this, you want to go this way. So it prevents us from going back like a dumb person, right? Okay, cool, cool. That's nice. Let's just say we modified the algorithm to put in the parent of the vertex for absolutely no reason, because just we might need it, we might not. Let's just put it there. We put it in there. Cool. It's still a DFS function, right? You navigate, but you just have the parent coming in for no reason. Cool, nice, awesome. So the same function, if it's not visited, you wanna visit it, which is true. And we have hijacked our whole function using a return. So it's like now the DFS traversal function returns if a cycle exists or not, which is a Boolean. So instead of printing, which is like printing the traversal, it now returns something. It returns true or it returns false, detecting, because it's you've hijacked the recursion using the true and the false, right? So what happens is if we haven't visited the neighbor, we want to visit the neighbor, and this is what that does. We visit the neighbor, but we say, hey, wait a minute. If that function, we're gonna pass on to the next step. I did my thing, and then I told the clone of me to go and do the same thing. So that guy does the same thing. But all of us in sequence have the goal of finding a circle. If my clone does his thing and tells me, hey, I found a circle for a cycle for some reason, I'm gonna be like, my clone found a cycle, which means I found a cycle. A cycle exists. So I'm gonna tell whoever called me that, hey, I found a cycle. And it's just gonna permeate. So it's like the function returns a Boolean, returns if we found a cycle or not. If while exploring in depth, because we keep exploring, right? If future exploration, don't ask me how just yet, I'll explain it. If future exploration results in me finding a cycle, awesome, I found a cycle. I don't need to explore anymore. You didn't ask me to explore the whole graph. You just asked me to find a cycle if a cycle exists. So if a cycle exists, I'm good. I'm done. Let's go back. Awesome. So if a cycle exists, return true. End of story. Just go back. Recursion exits. Go back. Right now, this is the interesting part. Okay, this is the crux. Now, I told you that we added in parent for no reason, right? So okay. I'm gonna move this block a bit. Okay, I told you that we added parent for no reason, right? So, okay, if if we don't, if we haven't seen it, we explore it. Cool. Else if, else means we have visited it, which means visitor of neighbor is 1, which means we've visited that neighbor, correct? What is the visited array used to do? The visited array is used to make sure we don't visit the parent again. What if the neighbor that was visited, right? The neighbor that was visited is not the parent. Well, that means we found a neighbor that was visited, but we didn't come from that neighbor, which means with like a road example, which means I'm at a city and my neighboring city has already been reached, but I didn't come from there, right? Now, if my neighboring city, if somehow my neighboring city got reached, but I didn't come from there, right? And I'm traveling the thing by myself doing the sequence of steps, well, it means that there's another way to reach that neighboring city because I reached it somehow, right? I didn't come from there, but somehow it's visited and I'm stuck here, meaning I visited that city through some path and now I'm at my location. And there is also a path to go there directly because it's my neighbor. Meaning I have a direct path because it's my neighbor, and I have some indirect path going through the loop because somehow I visited it, right? I'm traveling through edges. So I got from there to here somehow in some way, right? which means there exists a cycle. There's an edge, and some other sequence of edges exist through and where maybe you reach that place. So a cycle exists, right? That's the crux. So this is really where the program sort of ends. If this sequence exists, this is where the first cycle is detected. It finds it true, goes back, goes back, goes back, and then if you just did your DFS, and then this is like the main this is the main trigger, right? This is the main trigger, the for loop of all of the neighbors. If you explored all your for loops for neighbors, and this is like recursion inside, and you didn't find a cycle, meaning nothing. I mean, if your program hasn't returned by that point, it means you didn't find a cycle, right? Because nobody found a cycle. So then you say false. So like, hey, what? No cycle, right? And your sort of like your parent function that calls this function would be visited equals 0 or I mean, just make up this what you will. This could just be an empty array, and this could be if neighbor in visited, it's the same thing. Um, and you would do so you would traverse so for vertex in graph and this is self dot graph. So this is just the same thing for connected components. You would do if visited vertex 0, you would now since the now the DFS traversal function returns true or false, you would do if DFS traversal. You would do vertex first and the -1 for the parent. This is true. Return true. Then outside the for loop, if you just never return the true, return false. Okay, that's it. That's the whole cycle detection function with this tiny thing as the crux, right? And oh, we have the neighbors, so we have the parents as well. Now, if we were to do this using BFS, it would pretty much be the same algorithm. So I'm just gonna write it out really quickly so as to like not waste time. Now we're gonna do cycle detection using BFS. We're gonna do it a very similar way. We're gonna do do and the interesting thing is like I said, parent, right? Parent. Since the queue stores that stuff, we're gonna put in a tuple again. But the tuple is gonna be source comma parent. Sorry, it's gonna be um, vertex comma parent, which is -1. So instead of just pushing in the element, you'd have the parent stored there as well. And while q, I mean, it's the same code. It's literally the same code. I'll just leave this out so you can sort of understand what we're doing. Hop left, and here. So since we have a tuple in there, we can do let's say node this is me accessing the vertex, and so this is just me. This is me like doing this and this, and this and this. And we're gonna do if visited neighbor 0, it's unvisited. We're gonna visit it. We're gonna add it to the queue, and like I said, it's a tuple, so we're gonna go neighbor, and the parent is now node, right? So this is just basic BFS, right? Here we go elif parent not equal to neighbor. Which is the exact same thing I just told you in the DFS, the same logic, return true. The code exits outside the parent for loop, return false. Right? And yeah, that's about it. It's a giant for loop with a hijack, which breaks if you found a cycle. And your parent, this is the traversal function, by the way. Your parent function, just like last time, would be now you just make your visited array inside this. And yeah, once again, for connected components, you would go for vertex in self dot graph. Yeah, and you would same logic, just like this thing right over here. You would do if visited vertex if BFS traversal of vertex. We don't need the neighbor because the neighbor is just triggered inside the actual function. Sorry, we need to visit it as well. So if this is equal to true, return true. Same code. Outside the for loop, return false. All right, cool. Now you know how to cheekily insert this one segment to check if there's a graph, if it's a cycle using the parent, right? Yeah. Like I feel like this video has gone on for quite a bit. I might stop the video here and then in the next one talk about cycle detection on directed graphs and topological sort, because they're both on directed graphs, and some other complex stuff, algorithms like Dijkstra's. But yeah, that's been it for this one. Tried to keep it simple from the basics. Hope you enjoyed it. Hope it gave some clarity and helped you in some way. Drop a like, subscribe, and let me know what stuff you'd like to see on the channel. Please let me know if you've understood the stuff that I just talked about. And yeah, I'll see you guys in the next video. Hey, do. Bye for now. Have a great day.